In this lesson, we're going to cover Rolle's theorem and the mean value theorem. First, we're going to start with Rolle's theorem. It says, let f be a function that satisfies the following three hypotheses. Number 1, f is continuous on the closed interval from a to b. Number 2, f is differentiable on the open interval from a to b. And number 3, f of a equals f of b. If all three of these are satisfied, then Rolle's theorem states that there is at least one number c in the open interval from a to b, such that f prime of c is equal to 0. So we have three diagrams here where f is continuous on the closed interval from a to b. F is also differentiable on the open interval from a to b. And then you can see that f of a is equal to f of b for all three diagrams. So Rolle's theorem says that since all three of those hypotheses hold true, there is at least one number c in a to b such that f prime of c is equal to 0. So for this first picture, you can see right here, you have c, and at that point on the curve, you have a horizontal tangent line. So f prime of c is equal to 0. For our middle diagram, we have two places where the slope is equal to 0. That would be at this c value and also at this one. And then finally, for the third diagram, you have your horizontal tangent line right here, and there's our c value. And again, c is in the open interval from a to b, so it's not going to be on one of the endpoints. This example says, let f, and here's our polynomial. It's on the closed interval from 0 to 4. Find all numbers c that satisfy the conclusion of Rolle's theorem. I made a note, since f is a polynomial, therefore f is continuous for all real numbers, and therefore our first hypothesis, f is continuous on the closed interval from 0 to 4. Next, f is differentiable on the open interval from 0 to 4. And then finally, I plugged in the endpoints into f, and you can see when you plug in 0, you get 5, and when you plug in 4, you also get 5. So we've just shown that f of 0 equals f of 4. Since all three of these are satisfied, Rolle's theorem can be applied. So we're going to take the derivative of f, and also at the same time we're going to plug in c. So the derivative of this first term is 3x squared. The derivative of this term is negative 6x. The derivative of this is negative 4, and then the derivative of 5 is 0. And again, we're going to plug in c for all the x's. So f prime of c equals 3c squared minus 6c minus 4. And we're going to set this equal to 0. Bummer, I was hoping this would factor, but it doesn't, so we're going to use the quadratic formula to solve. And we get down to here, and then finally I'm going to plug this into the calculator. I'm going to plug in 6 plus the square root of 84 all divided by 6. And then I'm also going to plug in 6 minus the square root of 84 all divided by 6. So you end up getting negative 0.528 and then also 2.528. Remember, for Rolle's theorem, your c value needs to be in the open interval from 0 to 4. So that means we can cross out this option. And by Rolle's theorem, we have c equals 2.528, which is an element of the open interval from 0 to 4. Next, I have here the main use of Rolle's theorem is in proving the following theorem, which was first stated by the French mathematician Joseph Louis Lagrange. So, good old Lagrange. We have our mean value theorem. It says, let f be a function that satisfies the following hypotheses. Number 1, f is continuous on the closed interval from a to b. Number 1, f is continuous on the closed interval from a to b. Number 2, f is differentiable on the open interval from a to b. If both of these are satisfied, the mean value theorem says there exists a number c in the open interval from a to b such that f prime of c is equal to f of b minus f of a all over b minus a. So this probably looks familiar. You have your slope of a tangent line equals, and over here you have slope of a secant line. So right here, if you were to take this proportion, think of it as a proportion because you have one fraction equals an expression. If you were to cross multiply, you'll get this statement, b minus a times f prime of c is equal to f of b minus f of a. So that's an equivalent statement. Next, it says if an object moves in a straight line with position s, which equals f of t, then the average velocity between a and b is going to be this. So again, here's your average velocity formula, and that will be equal to your velocity at c, and that's going to be your f prime of c. Right here we have a note, ways to interpret the mean value theorem. At some time t equals c between a and b, the instantaneous velocity, or f prime of c, is equal to that average velocity. For example, if a car has traveled 120 miles in 2 hours, then the speedometer must have read 60 miles per hour at least once. And our last note here, it says there is a number at which the instantaneous rate of change is equal to the average rate of change over an interval. So here's our diagrams that I want to demonstrate the mean value theorem graphically. So for all three of these diagrams, they satisfy the conditions of the mean value theorem. They're all continuous over the closed interval. They're all differentiable over the open interval. So therefore, the mean value theorem can be applied. To apply the mean value theorem graphically, first we're going to draw our secant line between the endpoints. This line right here, we're going to think of the slope of the secant line. And we want to identify another point on this curve where the slope of the tangent line will be equal to the slope of this secant line. So it looks like that's going to occur right about there. So again, you have slope of the secant line and you have slope of a tangent line where they're equal slopes, meaning the lines are parallel. And then we go down here and this is going to be our value C, again where C is in between A and B. So this is graphically demonstrating the mean value theorem. We're going to do the same over here. Again, the hypotheses of the mean value theorem are satisfied, so the conclusion says that we can draw a secant line between the endpoints, and there should be at least one point on the curve where the slope of the tangent line equals the slope of the secant line. So in this case, we have 2 points on the curve that satisfy the conclusion of the mean value theorem. We have this value and this one, and both C values are in the open interval from A to B. Okay, for this last diagram, again, we start by drawing the line connecting the endpoints. So here's our secant line. Now we're going to look at the curve and identify another point where the slope of the tangent line equals the slope of the secant line. And again, for this picture, there's 2 points where that happens, where again, the slope of the tangent line equals the slope of the secant line. And here I just drew one more curve. I just want to point out, depending on the curve, you could have 1 point that satisfies the conclusion of the mean value theorem. You could have 2 points, or in this case, let's see, we have right there, right here, and right here. So here's a picture where you have 3 different points that satisfy the conclusion of the mean value theorem, and those 3 C values are in the open interval from A to B. This example says, identify whether or not the function satisfies the hypotheses of the mean value theorem on the given interval. If it does, find all numbers C that satisfy the conclusion of the mean value theorem. Our function is 2 square root of x, and our closed interval is from 0 to 9. I drew the curve of f right here from 0 to 9. So first we have f is a root function, therefore f is continuous on, and it goes from 0 inclusive to infinity. And therefore, because 0 to 9 is inclusive from 0 to infinity, we can state that f is continuous on the closed interval from 0 to 9. Next, we can state that f is differentiable on the open interval from 0 to 9. And since the hypotheses of the mean value theorem are satisfied, the conclusion of the mean value theorem says f prime of c equals f of b minus f of a all over b minus a. So I rewrote f of x as 2x to the 1/2, so we can take its derivative. So for f prime of x, you get 1 over the square root of x. Right here, we're going to use the notation f prime of c. So since f prime of x equals this, f prime of c is going to be 1 over the square root of c. Over here, we're going to f of b minus f of a all over b minus a, where 0 is a and 9 is b. So we're going to plug in 9 right here for x, and then we're going to plug in 0 right here for x. So we get 6/9, and 6/9 reduces down to 2/3. At this point, we have a proportion, so I'm going to cross multiply. And again, we're solving for c, so I'm going to divide both sides by 2. So root c equals 3/2, and very last step, we're going to square both sides. And we end up getting 9/4 or 2 1/4. And I wrote it out by the mean value theorem, c equals 2 1/4, which is an element of the open interval from 0 to 9. And again, I just want to go back to our original diagram and look at this graphically. If we draw the secant line between the 2 endpoints, and again, we think of the slope of the secant line between these endpoints, and then we look on the graph at 2 1/4. If we go up to the curve and we draw a tangent line to the curve at this point, and the slope of the tangent line should be equal to the slope of the secant line. For this example, we have f of x equals x over x plus 2, and our closed interval is from -1 to 1. So I wrote f is a rational function, therefore it's continuous for all numbers except for -2, and therefore we have f is continuous on the closed interval from -1 to 1. Next, we have f is differentiable on the open interval from -1 to 1. So to apply the mean value theorem, we're going to go f prime of c equals f of b minus f of a over b minus a. Here's our a, here's our b, and then to take the derivative, we're going to use the quotient rule. So we get 2 over x plus 2 quantity squared. Since this is f prime of x, we're going to take c and plug it in for x. Again, this is f prime of c, and then on this side, we need to do f of b minus f of a over b minus a. So right here, we have f of b. So I took 1 and plugged it in, and we get this fraction. Minus, this is f of a, so I took -1 and plugged it in. And then it's all over b minus a. Right here we have negative 1 over, and it's negative 1 plus 2, so negative 1 plus 2 makes 1. So negative 1 over 1 is going to be negative 1, and then times the negative is positive 1. In the denominator, we have 1 minus a negative 1. Those become a positive, so you get 2. We want these to have common denominators up here, so I'm going to multiply this by 3 over 3. So up here we get 4/3, and it's still divided by 2. So I'm going to put this over 1, and we're going to multiply by its reciprocal, or copy dot flip. And we end up getting 2/3. So now we set this expression equal to 2/3. Next, I'm going to divide both sides by 2. And at this point, we're going to cross multiply. So we get c plus 2 quantity squared equals 3. And we're going to square root both sides, put a plus or minus. And we end up getting c equals negative 2 plus or minus the square root of 3. Since c equals negative 2 minus root 3 is not in the open interval from negative 1 to 1, I have right here by the mean value theorem, c equals negative 2 plus root 3 is in the open interval from negative 1 to 1, so this satisfies the conclusion of the mean value theorem. This example says, suppose that f of 0 equals negative 3, and f prime of x is less than or equal to 5 for all values of x. What is the largest possible value for f of 2? Okay, so first, since f prime of x is less than or equal to 5 for all values of x, then we know that f is going to be differentiable and therefore continuous for all real numbers. Next, it gives us that f of 0 is negative 3, and then it says what's the largest possible value for f of 2. So that means our interval is going to be 0 to 2. So I just wrote that out, apply the mean value theorem to f on the closed interval from 0 to 2. So we have there exists a number c such that f of 2 minus f of 0 equals f prime of c times the quantity 2 minus 0. Again, using the mean value theorem in this format was noted on the previous page. So I made a little note, we're going to solve for f of 2. So we have f of 2 equals f of 0 plus f prime of c times 2. We're given f of 0 equals negative 3, so I plugged in negative 3, and then we have plus 2 times f prime of c. Since f prime of x is less than or equal to 5, we can then write f prime of c is also less than or equal to 5. And so then we can say that 2 times f prime of c is less than or equal to 10. Therefore, if we go back to this statement, we have f of 2 equals negative 3 plus 2 f prime of c, which is going to be now less than or equal to negative 3 plus 10, which equals 7. So finally, we can conclude thus the largest possible value for f of 2 is 7. This example says let f be a differentiable function for all real numbers with selected values of f at x given in the following table. So here you have your x values and then your f of x values. It says, must there be a value c such that f prime of c is equal to 5/2? Explain your reasoning. Okay, I wrote yes, since f of x is differentiable for all real numbers, it is also continuous for all real numbers. Therefore, f of x satisfies the hypotheses of the mean value theorem. Next, we want to look at these data points, and we want to see if there's two sets of data points where if we do f of b minus f of a over b minus a, that we'll get 5/2. So I want to use these two data points right here. So we have f of 1 is negative 2 and f of 3 is 3. So we can set up the conclusion of the mean value theorem. We're going to go f prime of c equals, and we're going to go f of b minus f of a all over b minus a. From the table, we have f of 3 is 3, f of 1 is negative 2, and in the denominator we get 2. So we get f prime of c is equal to 5/2. And finally, we write, thus, by the mean value theorem, there must be a value c where c is between 1 and 3 such that f prime of c is equal to 5/2. This example says the mean value theorem does not apply to f of x, which equals the absolute value of x minus 3 on the closed interval from 1 to 4 because we have these four answer choices. F is the absolute value of x minus 3, so I have our absolute value graph that's been shifted to the right 3. So this is our graph for f, and you have these different answer choices. Answer choice A says f of x is not continuous on the closed interval from 1 to 4, and you can see that the graph is continuous from 1 to 4, so the answer choice A will not be one of our answers. Answer choice B says f of x is not differentiable on the open interval from 1 to 4, and that's actually true because right here at 3 we have a corner, and you cannot take the derivative of f at a corner. So it looks like B is going to hold true. Finally, I just want to check f of 1 is not equal to f of 4. So we have f of 1 is right here. I believe it's a height of 2. And then f of 4 looks like it's a height of 1. So that is true, but that would not necessarily apply to the mean value theorem That would be if it was Rolle's theorem. And then finally it says f of 1 is greater than f of 4, and f of 1 is greater than f of 4, which again, mathematically is true, but doesn't apply to the mean value theorem per se. So our answer is going to be B. Alright guys, thanks so much for watching.